All right, hello everybody. Today we're going to take off where we left off last period, going into section 1.2, finishing that up today. I know some classes got farther than others, so you'll just have to adjust and take a look at your notes and see where we stopped. I believe most of us, if not every class, stopped at intrinsic versus extrinsic properties. So, quick reminder and review. Intrinsic properties do not matter on the amount of matter. So it doesn't matter if I have 2 grams, if I have 500 grams, the melting point and the boiling point are not going to change. They just are what they are. Extrinsic, though, does depend on how much matter you have, because there is a big difference between 5 grams and 500 grams or 1,000 grams. So it's going to change the volume, the mass, and the amount of energy needed to break those bonds apart. So intrinsic does not matter. Extrinsic does matter. So that's an example of where I said inexpensive. We don't really care what the price is or how much it costs when it's inexpensive because it doesn't really matter. Extensive, if it's expensive, we do care how much it costs. And we want to look at how much money it's going to be because the amount matters. So kind of some ways to remember the difference between intensive and extensive. All right, so I know some of us got to this, some of us didn't, but we're going to talk about physical properties first. So this is what is observed without changing the identity of the substance. So what that means is if you're looking at a piece of paper, you're able to describe what a piece of paper looks like. It's white, it's thin, it can be shaped into different shapes and whatever we need it to look like. But it's still paper, so it's not going to change what it is. Another example you could use is like cheese. Cheese has many different forms to it, but still cheese. It doesn't change, but it does have a certain melting point and boiling point. So that's not going to change regardless of what type of cheese it is. So there are more of those descriptive words that describe what it looks like. Physical change, though, occurs without altering the identity of the substance. So grinding, cutting, melting. So for example, if I take a piece of paper and I rip it in half, I now have 2 pieces of paper. Did it change what it is? The properties of it? No, it's still paper, but now I have 2 pieces of paper. If we go back to the cheese idea, if I take cheese and I put it on the stove, it's going to melt. It's going to be liquid cheese. Well, liquid cheese is still cheese. It doesn't change. Water is a prime example. It goes through these physical changes. So when it starts off as ice, it's in the solid form. And when it melts, it turns to a liquid. And then when it evaporates, it will turn into water vapor. It's still water. It's not changing what it is. It's just changing states of matter. So physical change, you're not changing exactly what the substance is, but you're alternating the identity. All right, so changes in state is an important example of physical change. So how does this differ from state of matter? A state of matters, they aren't changing. So when we talk about states of matter, so just like in the water example, it's still going through a physical change because it's going from one form to the next, but it's still that substance. When we have solid cheese, it's in a solid form. When we melt it, it turns into liquid, but it's still cheese. It doesn't change. So states of matter is super important when it comes to chemical and physical change. Physical change. Okay, we have our 3 types. So we have a solid, liquid, gas. Most of us should know that by now. So a solid has a definite shape and a definite volume, meaning that it is what it is. So that means those particles are super closely packed together. They are vibrating ever so slightly. So any solid object you have is vibrating. If it's such a slight vibration, you just aren't going to notice it. A liquid has a definite volume, but not a definite shape. So those particles are a little bit farther apart. They are allowed to flow across each other, and that's what allows liquid to pour out of different containers. But it does fill a definite volume. It does fill up a definite amount of space, but it can fill in whatever shape container we need it to fill. A gas, though, on the other hand, has no definite shape and no definite volume. These particles are moving as far away from each other as humanly possible, and they're flying across the room, and they just want to stay away all the time. There is a fourth state of matter, which is plasma. We're not going to worry about that. We don't generally study that in chemistry, so that one you do not have to worry about. So here's kind of a good depiction of each state of matter. So a solid is going to be very rigid in structure. Again, it's any solid, the table, your iPad, whatever you're using that is a solid object is a solid. It has that fixed shape because if we break it, it's now something different. It's two pieces instead of just one, but it's still in that fixed shape. It also has a fixed volume. It's only going to take up so much space, and it cannot be squished. So I can't squish something, a solid, and expect it to stay in that shape other than bust apart. Then liquid is not rigid. It allows it to flow. It has no fixed shape. I can pour it into whatever container I want, and it'll take the shape that it is. It does have a fixed volume, though, so there's only so much it can have, depending on how many or how much liquid there is. It also cannot be squished. You cannot squish water together because of the overall shape and how close those molecules are together. And our last one is a gas. It is not rigid in shape. It is not fixed, and not fixed shape at all, and it has no fixed volume. They fly around the room. They fly inside whatever container they're in, and they're constantly bouncing back and forth. These ones, though, can be squished. That's why we can pressurize air, and we can create aerosols and things like that that push liquid out. And gas is constantly being squished inside of a container. So air tanks are a prime example. It's just pressurized air inside of it and pressurized gas. Okay, so that was physical properties and physical change. So physical, real quick, physical properties is describing what that physical object may look like. A physical change is basically a changing of state of matter, cutting something, breaking it apart, creating, it's still the same substance, but it may be two of the same substance, or changing states of matter. So physical and change in physical properties. Now we're going to get into chemical properties, the ability to transform into a new substance. So chemical properties, the big difference between the two, physical and chemical. Chemical is always going to be making something brand new. A physical property, it's going to stay the same. It just may change what it looks like. So we're making something brand new. So the flammability of something, the solubility. Solubility just means the ability of it to be dissolved in water. Combustibility, the ability for it to catch fire or to explode. All that is a chemical property. The ability for it to change into something brand new. Chemical change occurs when a new substance is formed. So we also can call that a chemical reaction, because in a chemical reaction, we start with something called reactants. That's what goes into a chemical reaction, and products, and that's what comes out. So when I am baking a cake, I start with my reactants or my ingredients, and that is going into my batter. I'm mixing it all up, and it's going through a chemical reaction. And I throw it in the oven, and I am able to create a product, which is the cake. They are two very different things. Cake batter and cake, two very different things. And through that chemical reaction, we're able to make the cake that is being made. So you may also oftentimes hear me call it a chemical reaction instead of a chemical change. All right. There are some indicators that a chemical reaction is occurring. You will need to know these, so I would star these in your notes so that you don't forget to study these for your test next week. So 4 indicators of a chemical reaction. Bubbles. If bubbles are formed, that means a gas is being formed. So for example, if you ever done the lab where you mix baking soda and vinegar, it's going to bubble. And those bubbles is a gas being formed, that carbon dioxide. A color change. So if something changes color from clear to pink, that is a chemical reaction is occurring. It gets cloudy because it's forming a new substance. So anytime we get something that is cloudy in view, it is oftentimes forming something called a precipitate. A precipitate is a solid being formed after a chemical reaction. And the last one is heat or light being given off. So a lot of times in a chemical reaction, we're going to see a flash of light or a kind of an amount of heat being released out. And that will tell us that a reaction is occurring. So you will need to know these for your test next week. So bubbles being formed or creating of a gas, a change in color, gets cloudy because it forms a precipitate, and heat or light being given off. So here's some examples of a physical versus a chemical change. So we are dealing with mercury 2 oxide. So if we're looking at the physical property of mercury 2 oxide, it is bright red or orange red. It is odorless, as a crystalline solid, so it's a crystal shape, and almost soluble in water. So those are physically how you would describe it. Chemical property decomposes when exposed to light or 500 degrees Celsius to form mercury and oxygen gas. So here, since we have our Bunsen burner going, we are able to see that we are actually putting it through the reaction. We're going to break it up into oxygen and mercury. Now, if I was going to explain oxygen, the physical properties of oxygen, it's colorless, odorless gas, soluble in water. So that's what it physically looks like. It does not have a color to it. It is soluble. Chemical properties: supports combustion, reactions or reacts with many metals. So if I wanted to explain a chemical property of it, it can combust. It is needed to be able to light something on fire. Also, it reacts with metals very well. So if something oxidizes, that's because of oxygen. Mercury, physical property, silver white liquid metal. In the solid state, mercury is ductile and malleable. Ductile means being able to pull it into a thin rope. And malleable means to be able to roll it into a thin sheet and can be cut with a knife. Those are things I can physically do to it and I can physically see. Chemical properties: forms alloys with most metals except iron, combines readily with sulfur at normal temperatures, reacts with nitric acid and hot sulfuric acid, oxidizes from form mercury 2 oxide upon heating. So basically what that's saying is this is what happens during a chemical reaction. These are what mercury can do during a chemical reaction. So physical properties, what you physically see in front of you. Chemical properties: how does it behave? How does it act? What can it do? And then chemical change is looking at what did you start with? What did you end with? Creating something brand new. A physical change, we're just changing it from one state to another. Energy changes accompany all chemical and physical changes. So anytime we have some sort of change, there is going to be something that happens that goes along with it. So oftentimes it's going to be these examples of light, sound, and heat. So for example, if you take a piece of paper and you rip it, you're going to hear a that's a sound. We hear that. That's energy being released because I'm using energy to rip the paper apart. A lot of times, if you see something to explode, then you're going to see heat being released and light being released. So think of those fireworks like we talked about the other day. Fireworks, again, you can thank a chemist for your fireworks. That's a chemical reaction happening in front of you. Your energy is being changed. It's going to be released as a form of light. That allows us to see the pretty fireworks. And if you ever stand too close to a firework, heat as well, and sound. So, all of that is falling under a chemical change. Okay, so that's the difference between chemical and physical changes, chemical and physical properties. Now let's talk a little bit about mixtures. So matter can be a pure substance or a mixture. So a mixture is a blend of two or more kinds of matter. So each is going to retain its own identity and property. I like to use the example of trail mix. So we all have had trail mix of some kind, and you mix peanuts and M&Ms and raisins and all of those other good things into your mix. You mix it all together, you're creating a mixture. We're mixing two or more things together. But it's going to maintain its own properties because I can look and see and pick out the M&Ms or pick out the raisins and eat what I want to eat, and then maybe push off to the side what I don't want to eat. So a mixture, we're just mixing together two kinds of matter. Oftentimes we're dealing with a solution, so a solvent and a solute. Here we're going to talk about homogeneous and heterogeneous. So you also hear homogeneous also explained as homologous. Either one is fine with me. So homologous is the mixtures that are unified in composition. So things that make it really hard to separate between them. So we have salt water. So water and salt mixed together. It's really hard to separate water and salt without evaporating all of the water. There's no way really easily to do it without making all the water go away. So we also will call that a solution. So anytime we mix a solute with a solvent, then we are creating what is known as a solution. Heterogeneous mixtures are mixtures that are not uniform throughout. So for example, would be salad dressing. So if you ever get a time or you go to the grocery store, take a look at the salad dressing aisle and find a salad dressing like a vinaigrette or an Italian dressing. A lot of times you could tell how long it's been sitting there because you'll see it separate into the different layers. As long as those layers are there, they're always going to separate. That's why they say to shake well before you use it, is because it is this heterogeneous mixture. They don't mix uniformly, and they're eventually going to settle out. So down here I have a picture of the difference between a homologous and a heterogeneous mixture. Milk and coffee is going to create our homologous mixture. That's what we're used to. So we add coffee, milk, and sugar. We'll have a nice homologous mixture. It's all mixed together, but you can't really separate it. I can't add a bunch of milk to my coffee and then take it away if I add too much. It's there. You have to add more coffee to make it balance out. That would be considered a homologous mixture. If it was considered a heterogeneous mixture, there would be visible lumps of milk and sugar inside of your coffee, and you'd be able to pull them out and separate them very easily. So there is a big difference between homologous and heterogeneous. Homologous blends nicely, does not separate, is very, very, very hard to separate. Heterogeneous can be separated and can be easily distinguished between the different layers or different ingredients. Okay, so those are your mixtures, and then we get to our final slide, which is our pure substances. So a pure substance has a fixed composition. So every sample of a given pure substance has exactly the same characteristic properties. Every sample of a pure substance has exactly the same composition. So what a pure substance is something that every time you look at it, it's going to be the same. So a great example are the elements on the periodic table. Any of those elements, you look at one atom of that element, it's going to be the exact same as another atom of that element. It does not change. Table salt is another one. It doesn't matter which crystal of table salt you look at, it's going to look the exact same. The composition is the same. It's made of the exact same compound or elements, sodium and chlorine. It's not going to change. What it is what it is. It has a very fixed composition and what it looks like. So a pure substance, every single substance or sample you look at is going to be the same. It does not change no matter what. So a mixture, we're mixing two or more things together to create this mixture, whether it is homologous, which means it is unified and very hard to separate, or heterogeneous, meaning it's not uniform and it can be separated. And then we have a pure substance, which has a fixed composition. And when you look at one sample, it's going to be the same as the other samples, and it does not change. All right, so that's all I got for notes today. If you have any questions, let me know when I get back tomorrow. I'll be happy to go over it with you. Your homework tonight is section 1.2 review. It is posted on Google Classroom. There are physical copies in the classroom or on my desk as well. So make sure you grab one of those and try your best on it. I know it can be a little tough, but we will go over it tomorrow when you get into class and we'll finish up some more notes. And also make sure you're working on missing work and your test fixes worksheet as well. All right, let me know if you have any questions. Have a great rest of your day.